I'm going to talk about a modification to this. We're going to do what's called Gauss-Seidel. And here's how it works. Let's look at the algorithm for doing something like this. You say, I give my guess x naught, y naught, z naught, and then generate for me x1, y1, z1. But notice what happens. If I'm really on my way to converging to a solution, which, by the way, you are if you're doing an SDD matrix, then you could say, look, I pick my initial y and z, okay, and I get a new x. Now I go here and say, take my x and z for a new y. But wait a minute. Didn't I just get a better x? Why would I use my x naught when I just got x1, which presumably is closer? So this shouldn't be k. I already have k plus 1, so why don't I use it right now? Why wait one whole compute cycle when I have a better solution to x already? And now I get a better, hopefully a better y. And then I go to z, and instead of using xk and yk, I should use xk plus 1, yk plus 1. Trivial modification. It's called Gauss-Seidel. And I'm going to show you what happens if you do that in this code. So in this code, then, let me give you the results of that. So after one iteration, you just get 2 iterations. I just iterate away. And in fact, if you remember before, it took me 19 iterations to get down to numerical precision. Here it takes me 10. So it's almost twice as fast. Remember, in computing, a factor of 2 is speed. Look, you're getting the same answer. But a factor of 2, this is the right way to do it. If you can buy a factor of 2, man, you take it. Yeah?
In each step, you're getting closer in this method, yeah? Like I know it's converging the whole thing, but each step you're getting closer.
Well, there's no guarantee. It doesn't tell you exactly. You're guaranteed to converge. It doesn't mean that it doesn't converge in an oscillatory fashion, or, it can take a more circuitous route to this. Here, in this one here, this seems to be just converging monotonically down. But that's not a guarantee of the theorem. It could make it slower. You're guaranteed to converge. It's not guaranteed to be faster. So you see, you're on this ground where actually you're hoping to make use of stuff. You have this intuitive sense that it should go faster. Not guaranteed. But in practice, a lot of times you'll find that, in fact, it does, if you do Gauss-Seidel. Okay? Pretty nice. So now we have 4 ways to solve Ax equal to b. We have Gaussian elimination, we have LU decomposition, we have Jacobi iteration, and we have Gauss-Seidel iteration. Okay, so we got a number of techniques available to us at this point for us. Now, my hope is that Monday's lecture I'm going to talk about what's called conjugate gradient methods, which are fancier iteration techniques. Conjugate gradient, there's 2 sort of the predominant computational schemes on the market today are called biconjugate gradient method. Here, actually, let me write down 2 things for you you're going to become familiar with. GMRes. That's how you say that. Okay, don't go MRes. Res, just you drop GMRes. It's like people are so amateur when they don't say runga kutta, they say runga kuda, or something like that. You're like, you don't even know how to compute. That's what I usually tell them. GMRes, and what this is, generalized method of residuals. And what it is, that means, is fancy iteration scheme. Okay? All right. That's built into MATLAB. It's available for you. You go like this in its simplest form. Instead of a backslash, you do this. And by the way, if you do that, it's going to start guessing at zeros, and it'll start to get you a solution. So we'll look at that. The other one. Bicadistab. Okay? All right. By CG stab. Okay? It's like Latin. Say it again, conjugate. Say it in past tense. By CG stabbed. By CG stabbing. By CG. I will by CG stab. Okay. Anyway, by conjugate gradient stabilized method. That's right. It's a mouthful. That's why we say by GC stab. And again, what it means is super fancy iteration scheme. The sweet thing about these, and maybe you don't quite appreciate this, it's all built in. Writing these codes is actually a painful process. And there's no pain when you do it. Well, it's going to be a little bit of pain. Take that back. But compared to writing it yourself, painless. This is amazing computer power right here. Right? You're taking people who are professionals in this field, who've written pretty high-end codes for this stuff, who know that you're trying to solve really big systems of equations. You can even import matrices A that are sparse into this thing. It will set up the iteration. You can even give it a guess to say, look, I think the solution is about here. Take that. And the whole purpose of these programs is to try to get you that solution as quickly as it possibly can. And try. Can I beat n squared? Can I get close to n log n? How close to n can I get? And this matters a lot, by the way. This matters a lot professionally. Okay? So, for instance, if you're doing a global circulation model, which some atmospheric science people do, GCM codes, these are a repository, I think, at NCAR, the National Center for Atmospheric Research. You can actually download this global circulation model, which is sort of open access, public domain code, which is just a massive code for solving for atmospheric dynamics across the globe. Okay, how big a system do you think that is? How big a matrices do you think you're working with? Yeah, it's huge. You get to pick scale. What's my resolution? What's my resolution? You want resolution? Typically on the globe scale, if you start, is your grid cell a mile, 10 miles? Actually, sorry, kilometers. Okay? How many kilometers is their grid scale? And right, you don't want to make it too short because it's going to just keep costing you. Why does it keep costing you? Because inside of there are X equals B's you got to solve. You want to get it done in a finite amount of time. You want to get your PhD. You got to figure out fast methods to do it. And these are the kind of fast methods that really matter in those kind of problems. When you're talking about matrices that are just monstrously big, really matters a lot. And this is, in fact, the fastest way to do it. So anyway, they're there. So if you want to think about them, now we have 6 ways, right? Jacobi, Gauss, Seidel, generalized method of residuals, biconjugate gradient stabilized method. Okay, so six ways to solve AX equal to B. We were going to write a poem about this. My love for AX equal to B. Let me count the ways I love AX equal to B. And if you could do it in iambic pentameter and bring in all the stuff. Actually, I haven't told you this yet, but I'm going to tell you later. It's just like, if you can do that, then you don't really have to do any homework for the class. I just give you a straight A right there and call it good. The winning poem. So, all right. Anyway, listen, have a great Friday. I will see you guys Monday. And remember, think about that homework. Hopefully this lecture this morning helps get your thought around that. Don't submit anything until you make sure you've thought about that. All right.